my great pleasure to introduce our next speaker, Professor Zhang. Professor Zhang's research focuses on developing new static program analysis framework, and his talk will complete today's tutorial on program analysis on program tutorial on program analysis while graph-reachability.
Hello, everyone. Thank you for the introduction. So this is the second half of the tutorial on graph-reachability. And in the first part, Tom gave a gentle and nice introduction to the general idea behind the graph-reachability. And we have also seen some interesting client applications, such as program slicing, as well as point analysis. So moving forward, in the second half of the tutorial, we are going to take a deeper look at the graph-reachability formulation. In particular, we will be focusing on three topics on formulation, graph, and algorithm. That will be the three main themes of the second half of the tutorial. And I believe that we have 90 minutes to talk about the three topics. So to be more specific, and every graph-reachability problem instance contains these three aspects. Specifically, the formulation contains, basically, it describes your modeling of the underlying program analysis problem. And in the first part of the tutorial, we have seen, some matching parentheses language, and we have also seen a language for point analysis. So in practice, in general, the formulation in L-language reachability problem instance contains grammar. In most cases, it will be a context-free grammar. This is the first component. The second component is the graph, where graph contains the abstraction. Basically, it describes how you model the underlying program on the analysis. And usually, the graph will be a directed graph with edge labels from your formulation. Okay, those are the non-terminals. Sorry, those are the terminals from your grammar. And the last component, of course, is the algorithm. Basically, once you have the formulation, that is the grammar, and also you have the graph, and then you will pass on these two elements to the graph reachability algorithm, and then the algorithm will compute either the demand single source, single target, or the all-pair reachability information. So in the second half of the tutorial, we are going to focus on three reachability problem, formal language reachability problem instance. In particular, first, we will begin our journey with the Dyck-reachability problem, and we will be discussing a asymptotically fast algorithm for solving the Dyck-reachability problem. And then we will be moving on to talk about the formulation. In the second topic, we will be talking about a new formulation called the linear conjunctive language reachability formulation. In particular, we will be talking about why this is an interesting problem and what it can do in practice. Lastly, we will be talking about Dyck-reachability problem with a focusing on manipulating the underlying graph so that we can achieve better results. So this is basically the outline of the second half of the tutorial. Also, there's an alternative view of the three topics that we are going to cover. So we know that in the first half of the tutorial, we have talked about the CFL-reachability problem instance, and Tom also mentioned briefly about several extensions, such as weighted push-down systems and weighted nested word automaton. And in the second half of the tutorial, we'll be focusing on three problem instances, that is Dyck-reachability, indirections, and LCL-reachability. And this figure shows the relationship in terms of expressiveness of among those reachability variants. So first, the Dyck-reachability, which essentially describes a properly matched parentheses, that is the least expressive variant in this among everything. And then on top of that, Dyck-reachability essentially generates, essentially matches multiple Dyck-reachability problem instances simultaneously, which is a superset of Dyck-reachability. And on top of that, Dyck-reachability is a special class of the more general class called the linear conjunctive language reachability problem instance. Okay, so let's get started. The first topic is Dyck-reachability. And as I mentioned, we will be focusing on describing a faster algorithm for solving the Dyck-reachability problem instance. Before that, let's review what has already been covered in the first half. So we have already known the CFL-reachability framework, and we know that the CFL-reachability formulation admits a cubic time algorithm for solving the all-pairs reachability information. And recently, it has been shown that this cubic time complexity is indeed a lower bound for CFL-reachability. It's a conditional lower bound based on the hypothesis that there is no subcubic algorithm. There is no subcubic combinatorial algorithm for solving Boolean matrix multiplication problems, so that there doesn't exist any combinatorial algorithms for solving CFL-reachability in subcubic time. Okay, and but as I mentioned, right, we are going to first talk about a asymptotically faster algorithm for solving Dyck-reachability. How is that possible? So let's first revisit the complexity diagram. So the result applies to CFL-reachability, which is here. It states that in general, the general CFL-reachability problem has a cubic time lower bound, but it doesn't rule out the possibility that for a specific subclass of the problem, there exists a asymptotically faster algorithm. Okay, that is precisely the reason. So we will first focus on this important subclass of CFL-reachability, and let's see how we can do a better job. And let's briefly introduce some background on bidirected Dyck-reachability. There are two keywords in bidirected Dyck-reachability. First is Dyck-reachability. Second is the keywords of bidirectness. So first, let's take a look at Dyck-reachability. So Dyck-reachability, as we mentioned, is a subclass. Is a subproblem of general CFL-reachability, and as every CFL-reachability problem instance, it contains a grammar, which essentially is the diagramma that generates properly matched parentheses. The second component is the graph. So the graph is essentially a directed graph where the edge labels are from this grammar. Those are the terminals from the grammar. So those are the two elements of Dyck-reachability, and then we will have an algorithm for solving the all-pair reachability problems in the graph. Okay, and then let's move on to the second component in this concept, that is bidirected. So in a general setting, and we will have a directed graph where each edge is labeled by parentheses from the grammar. In a bidirected setting, all we need to do is to introduce inverse edges. So if there is a directed edge from A to B labeled by an open parens, and we introduce a inverse edge from B to A labeled by the corresponding closed parens, and we do the same thing for the closed parenthesis labeled edges, so that the entire graph will become bidirected. Okay, so that's the definition of bidirectedness and Dyck-reachability. And an immediate question is that why do we need to introduce the bidirectedness? Okay, so let me try to address it from two perspectives. The first perspective is that for many client applications, the bidirected treatment is indeed an over-approximation of the underlying directed problem instance. And I believe that in the first half of the talk, and we have already seen a case where for point analysis for C, and we need to introduce the barred edges in order to formulate the problem as a CFL-reachability problem. So here I'm going to introduce another application, that is alias analysis, field-sensitive alias analysis for Java. So for object-oriented languages, basically we want to know the alias analysis means that we want to compute a set of variables that can refer to the same object at the runtime. And based on this specific formulation, it just means that, of course, it's an over-approximation. So it implies that if two variables can have the same value, then potentially they are aliases. And we want to do it in a field-sensitive way. Okay, let's see how to do the modeling. So basically, we'll be focusing on these two types of statements. The first type of statement is what we call a read statement. So it means that we read out the field f of the object y and assign it to x. Okay, that's a read. So the program flows from y to x. And because it's corresponding to the field f, so we use f. Okay, we use the subscript f here. And the second statement is what we call write. So here, basically, we have the value of y, and we write it to the field f of object x. So the program flow is from y to x, and the label, the index is f. Okay, and lastly, we know that write has to occur before read, right? Because first you need to write something before you can read something. So we model write as open parens and read as closed parens. Okay, so far so good, and I hope that it's intuitive. But the problem is that if we take a look at these two statements, okay, so both of them are read statement. So x read out the value of z dot f, and y read out the value of z dot f. Okay, so essentially they have the same value, and based on over approximation, we should conclude that they are potentially aliases. But if we take a look at the directed graph, okay, directed graph modeling, we can see that x and y are not even reachable by the standard definition of graph reachability. Okay, then in order to model it as a graph reachability problem, one treatment is that we introduce the inverse edges, as I described in the previous two slides. By introducing those inverse edges, now x is reachable from y, right? Because we can see an open f and a closed f. And y is also reachable from x, so we can see an open f and a closed f accordingly. Okay, so this is indeed an over-approximation because it introduced some false positive node pairs. So let's take another look at why the cases where it will be imprecise. So there are 4 cases. The first case is x read the value of z dot f and y read the value of z dot f. Okay, that's basically the case that we have already talked about. In this case, it's precise because x and y are considered aliases, and in the graph, x is reachable from y and y is reachable from x. So we are good. So in the second case, we actually we first write the value of y to z dot f, and then we read out the value of z dot f and assign it to x. So in this case, we know that x and y have the same value, and based on the modeling, okay, so the value flow is from y to z and then z to x. So the arrow denotes, in this direction. And then by introducing the parentheses and labels, we will end up with a graph like this. Okay, in this case, the bidirected modeling is also precise because there is a path from y to x and there is another path from x to y. So note that here I omit the orange edges and I only gave the edges that can establish a valid Dyck path. But indeed, the graph is bidirected. Okay, I hope that this case is clear. And then the next case is actually the dual of the second case. Here we just read out, we first read out the value of x and then assign it to y. That's the dual of the second case. So they are essentially the same. Okay, the interesting case is the last case. So in the last case, both statements corresponds to a write. So we read out the value of x and y, and then we assign it to z dot f. In this case, well, we know that there's no correlation between x and y, right? Because we just read out the value of x and y, and we do not change the value of x and y. But based on the modeling of the bidirected Dyck-reachability, there does exist a path from x to y and y to x as well. So definitely in this case, right, y is Dyck-reachable from x and x is Dyck-reachable from y, but in reality, there's no aliasing information between x and y. So this is one case where the bidirected modeling introduce additional pairs which cause the imprecision in practice. Okay, so that's the first aspect of the bidirectness. Basically, it shows that it's an over-approximated treatment for some applications. The second aspect is that it also offers a view of over-approximation from an algorithm perspective. That is, if we take a look at the directed graph and its bidirected counterpart, we can see that what we do essentially in the bidirect graph is to introduce some yellow edges, okay? So the question is that if two nodes are reachable in the directed graph G, will they be reachable in G prime? The answer is yes, because G prime preserves all the edges in G. So, well, if they are originally reachable, they should be reachable in G prime as well, okay? Let's take a look at the inverse direction. Suppose that in your bidirected graph, two nodes are reachable. Can we somehow infer that the two nodes in the directed graph setting, are they reachable? The answer is no, because if we begin with the directed graph, right, we don't even know which edge is the, which edge in this case is the red edge, okay? So for each case, there are two types of edges, so there are 4 possibilities. And in some cases, these two nodes may not even be reachable, okay? Based on these 2 facts, we can conclude that if somehow we relax a directed graph G to its bidirected variant, and this bidirected modeling is an over-approximation of the directed counterpart. Okay, I hope that is clear, and we are going to revisit this concept later in the 3rd topic. All right, so I think we have enough background on the bidirected modeling. Then let's take a look at an example. So here we are showing a very simple tint analysis, and we are considering a Java-like language. And we want to do, well, essentially we want to compute whether or not the value of x can flow to y. So as we mentioned, we can model it a bidirected Dyck-reachability problem instance. And then we have the grammar, okay? Recall that the graph contains the program abstraction, and the language contains the formulation for the analysis that you want to perform. And then the 3rd element is the algorithm. So we pass the 2 elements onto the reachability framework so that it will compute, hopefully, a set of reachable pairs for your underlying problem, okay? So to formally state it, the problem that we want to address is that given a graph with n nodes and m edges, we want to solve the Dyck-reachability problem on this specific bidirected graph, okay? So because due to the, like the expressiveness slides, we can see that Dyck-reachability is a sub-problem of CFL-reachability. So definitely it can be solved by the traditional CFL-reachability algorithms. So I think this slide is very similar to one slide that Tom mentioned. And the essential idea for CFL-reachability algorithms is about inserting summary edges to the graph. So basically, you will begin with a normalized grammar, and then you are going to look for the corresponding edges in the graph. Suppose that you have a B labeled edge, and you have C labeled edge. Based on the grammar, you are going to insert another A labeled edge into the graph. So we call this red edges summary edges. If we somehow solve the problem in this manner, the complexity is qubit time, because in the worst case, you have quadratic numbers of such B edges, and for every edge, you need to look at all edges, right? All nodes in the graph in order to obtain those A edges. And therefore, the complexity is qubit time. And so we can slightly improve the asymptotical complexity by using the well-known 4-Racines trick, okay? So the focus of this topic is that we are going to introduce a asymptotically fast algorithm for solving the bidirected Dyck-reachability. So I can summarize the main idea using this quick example. Here we have a bidirected graph, right? Recall that the goal is to solve the all pairs graph reachability here. And the essential idea for CFL-reachability is to insert new summary edges. So in order to conclude that y is reachable from x, in a traditional setting, the CFL-reachability algorithm will need to insert those edges. Okay, we don't need to know the details, but we just somehow, I think, hopefully this figure gives you a sense that it's making the graph more complicated, okay? So essentially, it will take about 16 steps in order to conclude that y is reachable from x. So the algorithm that we are going to introduce, they take exactly the same input. And what we need to do is, first, we remove some edges, and then we collapse these two nodes, then we are done, okay? So in the faster Dyck-reachability case, it only involves 3 steps. Okay, so from this simple example, we can get a high-level idea. That is, the principal difference between fast Dyck and the traditional CFL reachability is that in the CFL reachability, we are inserting more edges. And in the fast Dyck case, we are somehow making the graph smaller. So the 2 nodes are reachable if and only if they are in the same representative node. Okay, so also I hope that this example can convince you that fast Dyck is intuitively faster than the CFL reachability counterpart. And then the next big question is why it is the case. Why can you merge the nodes instead of inserting edges to your original graph? So that is based on a very nice observation, which was discovered when I was a PhD student several years ago. So it turns out that we can somehow treat the reachability information, reachable node pairs, as a binary relation. For instance, here we have a bidirectional graph, okay, and we define a binary relation D, which contains a pair of nodes. So if 2 nodes are Dyck reachable in your graph, and we say that the node pair X and Y belongs to the binary relation D. Okay, that's the definition. And if we take a deeper look at the binary relation, we can see that it's indeed an equivalent class. Why? Because it's reflexive. Because the start symbol of Dyck language is nullable, S is nullable. It means that it contains all the self-cycles, means that XX, YY, ZZ, all of node pairs belongs to the binary relation D. The second property is that it's also symmetric. Recall that for all edges, we are going to augment the graph by inserting the inverse edges. So if X is Dyck reachable from Y, Y should be Dyck reachable from X as well. Therefore, the relation is symmetric. Finally, it's transitive. That's also obvious because the Dyck grammar essentially contains this transitive rule. Okay, by putting together these 3 properties, we can conclude that D is an equivalent class. Because it's an equivalent class, then instead of inserting summary edges to make the graph look more complicated, we can instead merge nodes in this equivalent class. So the essential idea is that in a bidirectional graph, we don't need to worry about the close price labeled edges, because every time it will be, there exists open price labeled edge in the inverse direction. So we only need to keep track of the open price labeled edges. And if there exists a node, in this case A, that has multiple have multiple open price labeled edges, and we can conclude that the 2 neighbors will be Dyck reachable, right? Because if here you have, because there always exists a close price labeled edge in the inverse direction. So that node can serve as a merging point. So all we need to do is to look for its neighbors, and then to look for its neighbors and merge them. So in this case, we can find 2 nodes X and Y, and we can merge the 2 nodes. And when we perform the merging, we only need to pay attention that we always merge the node with smaller degree to the node with a larger degree, where degree is measured by the number of neighbors a node has. Okay, if we keep doing this way, it will be very similar to the linear union finder data structure. So in the worst case, there are m edges in your graph, and we say that an edge is involved in a merging if the previous slides, this triangle diagram happens. So of course, every time when an edge is when an edge is involved in a merging, there always exists a node in your graph whose degree has been doubled, and each edge will be involved in edge merging for at most log n times. Okay, that's the high-level analysis. If we follow this claim, we can conclude that the algorithm has a m log n time complexity. In practice, most of the graphs are sparse, so this algorithm runs in linear algorithmic time in practice, which is faster than the traditional CFL-reachability algorithms, which runs in cubic time. So here I don't give any, I don't think that I have time to show the experimental data, But I hope that by having this high-level discussion, I can convince you that it's indeed a faster way to do the Dyck-reachability computation. So this result, n-log n result, is from, let's say, 8 years ago. And recently, the algorithm, the complexity of the algorithm has been improved to almost a linear time by these authors. That's to me, that's a very interesting result. Okay, that will conclude the discussion on the first topic. So in the first topic, and we have talked about a faster way to perform Dyck-reachability computation. So let's move on to the second topic. So in the second topic, we will be focusing on linear conjunctive language. In particular, we will be focusing on its formulation. So to motivate the linear conjunctive language reachability, let's review what has been covered so far. So in the first topic, we have talked about intent analysis via Dyck-reachability, where we use parentheses to match field read and field write. And we have the Dyck grammar. And once we have these two components, and we will throw them to the reachability framework. That's essentially a a reachability algorithm. The algorithm will compute the all-pass reachability information in your input graph. Okay, but in practice, the program can be far more complicated than this one. Okay, because in practice, the program can contain function calls and returns, right? It can also contain, let's say, pointer reference and dereference, as well as field, log and unlogs. So suppose that we have a we have a program like this. Essentially, this is it's almost the same as the previous one. The only difference is that instead of assigning the values directly through field read and write, we assign the value through a function call. So if we model this graph, we can see that in the first, in this statement, we assign the value of x to a.f. That's precisely what we will do in the Dyck case. And then it invokes this function, getF, at line 8, okay? And within this function, we assign, we read the value of, we read the field f of this object and return it to the variable y. So if we model this as a graph reachability problem, and we can see that now we have yet another Dyck language involved in this whole thing. So the bracket represents field read and write. We have already talked about that. And the parentheses corresponds to function calls and returns. And we know that in order to do context-sensitive analysis, the function calls and returns must also be properly matched. Okay, if we express this property in a formal way, we will end up with two Dyck languages, where the first Dyck language describes the matched field read and write, and the second language corresponds to the function calls and returns. Okay, essentially what we want is an inter-Dyck language where we use this special symbol to denote the interleaving of two Dyck languages. Interleaving means that the two Dyck languages can be arbitrarily interleaved. Like in this case, we have open brackets, open parentheses, and close bracket and close parentheses. Okay, so here is the graph abstraction. Here is your program formulation, and hopefully we will have a reachability algorithm that can solve this problem. Okay, so before we dive into the technical details, let's rephrase this problem. So technically, the problem that we want to solve is that given a graph with n nodes and m edges, we want to actually solve the inter-Dyck reachability problem. Okay, where inter-Dyck language is defined by this grammar. Okay, so what's the catch? What's the problem here? The problem here is that this language, okay, if we revisit this language, we can see that this language is not a context-free language. So essentially, context-free language is not closed on the intersection. So we cannot use the closure property to prove that D is a context-free language. Indeed, we can use pumping lemma for CFLs to prove that D is not a context-free language. Okay, so if it is not a context-free language, how could we use existing result to solve it? Okay, that seems to be a big question. But because we are PL researchers, okay, so we don't worry about those hard problems. So indeed, Tom shows that this problem, Dyck-reachability problem, is undecidable. So again, right, in PL research, most of the problems are undecidable. So we don't worry about undecidable problems. All we need to do is to, relax the problem a little bit and provide an over-approximated solution. So in this case, we can use CFL to over-approximate the previous non-context-free languages D. Okay, how could we do that? So recall that the precise language that we want to deal with is the interleaved Dyck language. And it turns out that we can use regular language to over-approximate one of these context-free languages. In this case, we can use the regular language to over-approximate the first Dyck. Okay, then the language D prime becomes a context-free language intersect with a regular language. Okay, from textbook, we know that CFL is closed on an intersection with a regular language. Therefore, D prime is a CFL. Okay, so if it's a CFL, then we precisely know how to do it, right? We just throw it to the standard CFL-reachability algorithm, and we can get some results. Okay, that's one way to do the over-approximation. And we can also be more aggressive. So we can, well, more aggressive means less precise, okay? So we can also use standard graph-reachability, where we don't even need to worry about the underlying labels, okay? We just use, let's say transitive closure to over-approximate this Dyck-reachability problem. Then we will end up with another language, D double prime. And of course, D double prime is also a CFL, is a context-free language, because standard graph-reachability is a subclass of regular language, right? So it turns out that we can derive 4 variants based on the reasoning. So here, I denotes context insensitive, where essentially we use standard graph-reachability to over-approximate one of the Dyck. And R here represents the regular language over-approximation of one of the Dyck languages. Because we have 2 Dyck languages, so we have 4 variants, okay? And all of them are CFLs, so we can use CFL-reachability to solve the problem. And the complexity is slightly subcubic. Okay, that basically summarizes how to solve the problem in a traditional setting. And next, what we are going to discuss is a new class of language. Again, whenever we discuss something new, we need to ask why, right? Why do we need to introduce a new language? So here, I'm going to invite you to somehow check out the rationale behind the traditional CFL-reachability. So in the traditional CFL-reachability setting, recall that our target now is try to solve and, well, try to some extent, solve an undecidable problem, where the undecidable problem is the Dyck-reachability problem, okay? So to solve the problem, it essentially contains 2 parts. The first is the algorithm, okay? How do you solve the reachability? How do you solve the reachability problem if you have the graph and the formulation? The second component is actually the algorithmic formulation. That is, you have a specific a grammar representation of your underlying problem. In the traditional setting, right, we have two components. In the traditional setting, we are over-approximating the grammar, right, like what we have already been discussed. Okay, therefore, if we combine these 2 components, we are over-approximating the harder problem on Dyck-reachability. Okay, so the next work that I'm gonna introduce offers a new perspective of solving this, of over-approximating this problem. Okay, the new perspective is that, well, because there are 2 components here, right? So in the traditional setting, we are over-approximating the right component. Okay, in the new perspective, we are over-approximating the left component. Okay, so here we are going to discuss an algorithm. We are going to discuss a framework that we have a precise formulation. Okay, we are going to introduce a language that can precisely describe Dyck language, but the algorithm is just an over-approximation. Okay. So what is the language? The language is called the linear conjunctive language. As I mentioned, it can precisely describe the Dyck language. And it's a linear language because on the right-hand side, it contains some terminals. Okay, so let me try to explain the semantics of this rule. So here we will see a special ampersand sign. That just means and. Okay, it means simultaneously. Okay, so in order to generate a non-terminal A in this language, there must be so two constraints must be satisfied simultaneously. The first constraint is that the underlying string has to begin with terminal B, and then the remaining part should be derived from another non-terminal big letter B. And at the same time, the last character should be small letter c, and the remaining part should be derived from its non-terminal C. Okay, and it turns out that this language has a very nice closure property. That is, they are closed on all set theoretical operations, including inclusion. Okay, therefore we can prove that this language belongs to linear conjunctive language, because all we need to do is to design a language to match Dyck, and another LCL to match another Dyck, and due to the closure property, we can prove that the inter-Dyck language is also in this LCL class. Okay, so we can also picturize everything. So essentially, an equivalent model for linear conjunctive language grammar is called the Trellis automaton. So essentially, they are describing the same idea. So in this Trellis automaton, the non-terminals will be represented as the square boxes. So in this case, we have an input string of A1 to A4, right? So in the first step, all the terminals will be initialized to a non-terminal, and then we combine two non-terminals, okay, and to generate a new state. Okay, that's why we have this triangle representation. And how to interpret the grammar? That means that in order to generate a apex node that is labeled by non-terminal A, there has to be two constraints. The first constraint is that the first letter should be B. Second is that the remaining part should be labeled by another non-terminal big letter B, meaning that the big letter B should be somewhere here. Okay? At the same time, the last character should be small letter. Well, last character means that A4 here. The last character should be small letter C, and the remaining part should be derived from another non-terminal C, meaning that C is somewhere here. Okay, that's why we have this triangle representation. And basically, the information will be propagated through the triangle, and then we need to all we need to do is to check the state of the topmost, the apex nodes, and to know that whether or not the language, the underlying string belongs to this language. Okay, that's the essential idea. So the next question is, how do we generate a set of LCL rules to do the graph-reachability formulation problem? So it turns out that it's not very straightforward, and I will omit the details here. But the essential idea is that first we need to program an equivalent model called deterministic, simple deterministic Turing machine, and then we use a Turing machine to automaton translation to get a set of LCL rules, and then we use the LCL rules to do the graph-reachability computation. Okay, but I will show an example here where the example is essentially the same as the previous example that we just saw. So in a chain graph case where we have we only have one path between any two nodes, and each edge label will be first initialized to a non-terminal, right? And then based on the LCL grammar, recall that for all the LCL grammars, they can be characterized, they can be divided into two cases, where the first is the initialized rules, where it takes a terminal label as input and generates a non-terminal label. Okay, so the second type of rules is from 5 to 17, where we take two non-terminals as input and then generate a new non-terminal. Okay, so that corresponds to this triangle representation. If we have left states, we have right states, and we go back to the previous slides and to check what output state it should be, and then we keep on populating the reachability information. Then we need to check that whether or not there is an accepting state between these node pairs to conclude whether or not they are LCL reachable from each other. Okay, that's the essential idea. So it turns out that this algorithm is more efficient than in terms of the complexity, it's more efficient than the traditional CFL setting. Okay, let's revisit this diagram again. In the traditional CFL-reachability setting, right? Once we have the non-terminal edge B, and we are going to look for another non-terminal edge C, right? The problem with this process is that there is no shortcut because all of them are non-terminal edges. They are generated on the fly during the computation. So before that, well, before you actually compute everything, there's no telling that how many non-terminal edges will be there. Therefore, you have to look through all nodes in order to find such C edges, okay? But in the LCL case, recall that this language has a very nice linear form. It means that, like we can see here. So for each component, we can always find a terminal, right? So terminal labeled edge corresponds to original graph edges, meaning that they will not change when, as you compute more reachability information, okay? So in this case, once we have this non-terminal edge B, and we only need to take a look at, the neighbors connected by the original graph, and then, well, of course, we need to do it twice, right? Because we have, like we have two components in the LCL. And then, if we somehow we can do it twice, then we can conclude that there is another non-terminal edge A from these two nodes. Okay, so if we can always do the computation this way, and it turns out that the complexity will be slightly better. The reason is that for all the non-terminal edges B, now we don't need to look for all nodes in the graph. Instead, we only need to look for the neighbors of this particular node V. Okay, well, the neighbors is measured by the degree of a node, and if we put together everything, we will end up with the complexity of Mn. Okay, so in practice, if the graph is sparse, and the asymptotical complexity of this algorithm is in coadjective time, which is slightly which is better than the qubit time CFL-reachability algorithm. Okay, so again, I didn't give any empirical evaluation here, but based on the empirical evaluation, we can see that LCL-reachability is more precise and faster than the CFL-reachability over approximations. Okay, so that will conclude the second topic. In the second topic, we basically focusing on a new class of language that can be used to precisely model the underlying CFL-reachability, underlying Dyck-reachability problem. Okay, then let's move on to the last topic. In the last topic, we are going to talk about, the remaining task to cover is that we want to talk about the Dyck language itself. And instead of talking about the algorithm for solving this problem, we want to do something interesting on the graph. Okay, so to basically, again, to understand the background, we can say that Dyck language, as we mentioned before, it's a hard problem, and indeed it's an undecidable problem. So previous effort, including LCL-reachability, we only focus on, finding smarter or better algorithms or better over approximations for solving this problem. Okay, and recently, from these authors, and it shows an interesting new perspective. Okay, yet another new perspective for solving the to some extent solving the Dyck-reachability problem. So the rationale is that basically there are two parts, right? For the Dyck-reachability, the first part is what is the how powerful your algorithm can be, right? So in the previous two topics, we have gone through a few over approximation algorithms for solving the Dyck-reachability problem, but what we left is the input graph. recall that input graph is also an input for your reachability algorithm, right? So the question that we have been thinking about is that can we do something on the input graph such that we can improve the existing, all of the existing graph reachability algorithms. By manipulating the input graph, I mean that removing some useless edges in the input graph. So we know that we are solving a reachability problem, right? And there are many edges in your graph, and some edges will be useful, meaning that some edges will be contributing to certain interdike passes. Of course, some edges will not. So those edges are useless edges. If somehow we can remove those useless edges, it will improve the performance of the whole framework. Okay, then let's talk about the specific benefit. The first benefit should be clear, because if somehow we are successful to reduce the graph, then your algorithm basically can work on much smaller graphs, right? Of course, if you work on smaller graphs and you are improving the scalability, right? Because your algorithm will run faster, presumably. The second benefit, which is more interesting, that by removing some edges in your graph, indeed, you can improve the precision of existing approaches. Why? Because we are trying to address an undecidable problem, and whatever we do is over-approximation. Okay, let's take a specific example. In this example, we have an interdike reachability problem instance, where if we take a look at these two specific edges, there will be two passes from X to Z. Okay, yeah, from these two nodes. Okay, so from this picture, we can see that there's no valid interdike path between these two nodes. Okay, but unfortunately, existing algorithm, okay, because they are all over approximations, existing algorithms, including LCL-reachability, will conclude that these two nodes are reachable. Of course, in principle, we are not supposed to understand why they will introduce this over-approximate, this false positive pairs, right? Because if you can do it generally, then you are able to solve the undecidable problem. Okay, so but it turns out that somehow we can magically mutate the reduce the graph, and we can improve the precision. In particular, if we apply the idea of graph simplification, and by the way, I'm going to introduce the graph simplification in a minute. If somehow we can reduce the graph, apply the idea, then we will end up with a graph like this. Okay, so this graph is pretty interesting. Why? Because it's a chain graph. Okay, in a chain graph, the reachability problem becomes the parsing problem, right? And because we can easily show that the two nodes, right, this node C is reachable from A if and only if this underlying string can be parsed properly. Okay, and although LCL reachability problem is undecidable, but the language parsing problem can be decided in quadratic time. Okay, so in principle, in this case, LCL will precisely conclude that these two nodes are reachable. Okay. Okay, so that's okay. And if we have a graph like this, we will have no false positive node pairs. Okay, that's the benefit of graph simplification. And so the next big question is that how can we remove the edges in the input graph? Okay, that's actually the interesting idea behind the graph simplification. Okay, then to describe the idea, let's take a look at this hypothetical example. Okay, so recall that the essential idea of graph reachability is to remove some useless edges. Okay, in this case, we divide all edges into two categories. One is non-contributing edges. Formally, it just means that an edge that will not be in any interdike paths. Okay, so from this figure, this graph contains 5 edges, and which edge is interdike contributing? So it should be this edge, right? Because The reason is that, because that's open 9, it's a closed 9, closed parenthesis labeled by 9. And we don't have any matching, open 9 edges in this graph. So this edge is not inter-die contributing. And what are the contributing edges? Okay, there are four edges. Okay, why? Because we have seen an inter-die path between these two nodes. Okay, so the definition of contributing edges is that the edge will be at least one inter-die path. So formally, graph simplification is about computing a set of non-contributing edges and get rid of them. Okay, so let's state it formally. The specific problem that we are trying to address is that given a graph with n nodes and m edges, we want to remove all the non-contributing edges for indirectly. In this particular example, we want to get rid of this closed 9 edge. Okay, so before we dive into details, I'd like to invite you to think about what exactly is the problem that we are working on. So currently, right, we are talking about how to removing the non-contributing edges. In order to remove those edges, first you need to compute, right? You need to exactly know that what are those non-contributing edges in your graph. And what is the underlying problem? What is the end goal of this graph simplification? So the end goal of this graph simplification is that we want to somehow improve the solving experience for the inter-die language reachability problem, right? Okay, then what's the relationship between these two problem instances? Okay, which one is harder? Okay, so let's take a look at them one by one. Okay, suppose that, recall that this problem is undecidable, right? Okay, suppose that you have a magical way to solve this problem. Does that imply that you can compute all the non-contributing edges in the graph? The answer may be probably no, okay? Because it depends on how you solve it. If you using the traditional dynamic programming style algorithm to solve it precisely, yes, you can use some tracing techniques to compute the non-contributing edges. But if you solve it in some non-trivial way, maybe it's not possible to retrieve all the non-contributing edges, okay? That's an open problem. But how about the inverse direction? Suppose that magically you have an algorithm for solving all the to find all the non-contributing inter-die edges in your graph. Does that imply that you can solve this problem fully? Yes. Why? Because for any inter-die reachable pairs like S to T, all you need to do is to insert some auxiliary, edges, right? For S, you can insert an input open parenthesis labeled edges, and for T, you can insert corresponding closed labeled edges. And the two nodes S and T are reachable. Well, T is inter-die reachable from S if and only if these two auxiliary edges are, Dyck contributing, right? Because you claim that you can magically solve this problem, it means that you can solve this problem as well. So based on the discussion, we can see that the second problem is at least as hard as the first one, okay? So that brings an interesting perspective, right? Because if we put together everything, and what I'm trying to argue is that in order to tackle this undecidable problem, and we have a new way to simplify the graph such that we can achieve better precision and performance. But now, by taking a deeper look at the problem, it seems that we are addressing an even harder problem, right? That doesn't make much sense, okay? How to make it work, okay? The magic here is that, instead of computing all edges, we only compute a subset of non-contributing edges. In some sense, it's another way to state that it's an over-approximation, okay? But recall that the requirement is that we want to compute the subset fast, okay? Because if we solve it as a CFL-reachability problem, it will probably defeat the goal of graph simplification because your algorithm may be as expensive as the original, reachability algorithm. Okay, then let's take a look at it and to see why it is possible. So we will be using this graph, okay? So in this graph, we know that there's an inter-die path from A to C, okay? If we take a look at this guy, open 8, okay, we know that open 8 is an inter-die contributing edge in this graph. because it has been involved in the interdike path from A to C. Okay, and if we revisit the definition of interdike, it just means that interdike considers the interleaving of multiple Dyck languages. Okay, so that means that what happens for the bracket labeled edges has nothing to do with the parentheses labeled edges, right? If this parenthesis labeled edge is contributing edge in the interdike path, if we get rid of this bracket labeled edges, this edge should be Dyck contributing from A to C, right? So that's the first observation for a interdyke language, which essentially represents the interleaving of multiple interdyke languages. And if we take out one component, meaning that we take one L from this interdyke language, and we construct a L graph, which essentially we label everything else as epsilon, and we collapse the nodes. Okay, so if we somehow construct such an LX graph, we can claim that if an edge is interdyke contributing in the original graph G, it should be Dyck contributing in the corresponding LX graph, right? So the problem then becomes that computing the the Dyck-reachability in the LX graph. Okay, so how can we do that? Okay, apparently we can solve it using the general CFL-reachability, right? But as mentioned, if we treat it as a CFL-reachability problem, it will basically involve a cubic time solution. Recall that this is a directed graph. Okay, so unfortunately, Dyck-reachability also has a cubic time lower bound. So theoretically, we cannot solve it faster. Okay, then what is the remedy? So basically, we will invite our old friends of bidirected Dyck, right? Because as we see, bidirected Dyck is actually an over-approximation of directed Dyck. Okay, so what we need to do is that originally we have this directed directed Dyck graph. All we need to do is to introduce the corresponding inverse edges and make this graph bidirected. Okay, in this case, all we need to do is just to flip the close parenthesis labeled edges, because every time we have two edges, right? So in this case, we have a close 8 from this node to that one. And in the bidirected graph, we will only show the open parenthesis labeled edges from C to this, from E to this big node. Okay, and we can see that because it's a bidirected graph, right? And we have our old friend, right? We have this fast Dyck. We can solve it, in a very efficient manner, and by merging those two edges. Okay, so if an edge is somehow involved in this merging process, we can somehow conclude that the edge will be contributing to a Dyck path in this bidirected graph. Okay, because that's essentially how you conclude that these two nodes are Dyck-reachable in the bidirected graph. That's the essential idea of graph simplification. Okay, before we show an end-to-end, process, I'd like to invite you to take a look at this over-approximation perspective. Okay, so in the graph simplification problem, essentially what we want to compute is that in the LX graph, we want to compute a set of Dyck contributing edges, right? Because if we know the Dyck contributing edges, we definitely know non-Dyck contributing edges. Okay, but this problem, although it's decidable, but it's somehow expensive. And what we do is that we take a faster path, and we model it. We relax the problem and model it as a bidirected Dyck-reachability problems. And now with the fast Dyck algorithm, we are able to compute a superset of the Dyck contributing edges, right? Because Dyck-reachability, bidirected Dyck-reachability is over-approximating the Dyck-reachability, okay? But the result itself is not interesting, because what it tells us is that if the bidirected Dyck-reachability algorithm concludes that an edge is contributing, okay, it may or may not be Dyck contributing in the original graph. Okay, that's the beauty of static analysis. So static analysis can only give one-sided answer. right? The interesting aspect is the flip side of your answer. So if an edge is non-Dyck contributing, okay, in this case, it represented the elements in the green area, right? So in the green area, everything is non-Dyck contributing in your original graph. Somehow, if you can, of course, we know that how to compute the bidirected Dyck contributing edges, right? So if we compute a complement of this set, we will end up with some node pairs here, and for those edges, we know that they will definitely not be Dyck contributing to the original graph. Okay, so putting together everything, and let's try to wrap up. So the original problem that we want to solve is that we want to improve the inter-Dyck-reachability solving by contributing the by computing the non-inter-Dyck contributing edges. We have two levels of relaxation. First, we relax it to a Dyck-reachability problem on the LX graph. Okay, and then the second level of over-approximation is that we relax the directed Dyck-reachability to bidirected Dyck-reachability. Okay, and because we have this fast Dyck algorithm, so we can compute very efficiently the set of all non-Dyck contributing edges. Okay, we don't care about the contributing edges; we only care about the non-contributing edges. And by showing, with the reasoning from the previous slide, we can conclude that whatever we get here will definitely be non-Dyck contributing in this LX graph. Okay, and by a similar claim, we can say that those non-Dyck contributing edges will definitely be non-inter-Dyck contributing in your original graph. So recall the purpose of graph simplification. We want to get rid of useless edges, and those non-inter-Dyck contributing edges are useless edges, so we can get rid of it. Okay, so that basically shows the end-to-end result. Using this with the help of fast Dyck for this input graph, we are able to remove this edge, and by previous slides, we know that it improves the performance and it improves the precision as well. Okay, so what is the time complexity? It depends on the underlying Dyck, fast Dyck algorithm. So in the original version of graph simplification, and we use the old version of fast Dyck. Okay, therefore the simplification takes m log n time, and the result has been improved. So in the newer version, and thanks to anonymous reference, and the reference pointed out that we can use the optimal Dyck algorithm to speed up the process. And yes, it turns out to be the case. So we can also use the optimal Dyck results and to do the graph simplification in almost a linear time. Okay, so that summarizes the three topics. Okay, so to sum up, we have talked about three aspects in graph-reachability formulation. That is the formulation, okay, that is the grammar, the graph, how to simplify the graph, and then the algorithm. We have talked about the fast Dyck algorithm, the principal idea behind the fast Dyck. And this picture shows the corresponding relationship among these three valence. Okay, so that summarizes the recent development. Finally, let me take. I think we still have maybe 30 minutes, right? Okay, yeah, 25 minutes. Yeah, let me briefly mention some future directions. And to me, there are two interesting future directions. The first direction is the theoretical development. Okay, so if we revisit this figure, we can see that this inter-Dyck problem is undecidable. Okay, but as a PL researcher, we do not worry about undecidability, right? Because in practice, we can always over-approximate or relax the problem to make it decidable. So what is the other direction to cope with the undecidability? The other direction is that we can also find some special cases, okay? And maybe on these special cases, the problem will become decidable. And then the requirement is that, of course, you don't want to find a trivial sub-problems. We want to find some meaningful sub-problems. So in particular, for the inter-Dyck case, recall that inter-Dyck, in this case, we are considering the interleaving of two Dyck languages. We can relax the problem a little bit. We can consider the sub-problem. That is, we can, so we know that in general, Dyck-reachability is hard to solve. But if we consider the Dyck language of only one type of parenthesis, I think that's also related to the one of the questions occurred in the first section. Okay, so if we consider only Dyck language of one parenthesis, and we will see that it will dramatically simplify the problem. Now, of course, we also need to consider the bidirected version. Okay, putting together these two definitions, we will see that the problem will become a lot easier. Okay, so let me first illustrate why this bidirected D1 reachability is essentially simpler. Okay, so the main reason is that if we consider multiple parentheses, then you have to employ a stack to match the parentheses, right? Because think about the parsing problem. So whenever you have a closed parenthesis, you will look for the top element of the stack and then to match, right? But if we only consider one type of parentheses, that stack is unnecessary, okay? Because all we need to do is just do counting, right? Because there is no distinguishing between the different parentheses types. So if you see an open parenthesis, you just say that, okay, you increment a counter. Otherwise, you decrement a counter, okay? The only requirement is that, okay, there are two requirements to meet. The first requirement is that in order to recognize a Dyck string, the overall, right, the overall weights or eventually the counter should be 0, okay, because that shows that you have equal number of opens and close. Second constraint is that at any point in any prefix of your string, the counter should stay non-negative. It should be 0 or positive, okay? But anyway, this is a counting, it becomes a counting problem. But if we apply this idea into graph-reachability setting, it's slightly more complicated because in a graph, you can have cycles. If somehow you are considering the counting for two Dyck languages, it will somehow become slightly complicated, okay? So to understand it, let me show you a quick example. So in this case, we have inter-Dyck path, right? And then we want to do the counting for two Dyck languages, and we use x-axis to denote the counter for parentheses, and we use y-axis to denote the counter for brackets, okay? So first, we have this open parenthesis, then we move from 0, 0 to 1, 0, and then we have an open bracket, then we move from 0, 1 to 1, 1, okay? And then so so basically we can keep continue this process, right? And if eventually, right, the path go back to the original point and it does not enter some negative, negative areas, and we can conclude that this is a valid inter-Dyck path. Okay, but as I mentioned, right, if your graph contains cycles, it will make this, it will make the maximum value of these counters arbitrarily large, which is problematic. So the main insight behind this bidirected D1 is that with the bidirected setting, and we have very interesting shallow path property. Intuitively, it means that a path between 2 points, a path can go back and forth, between these 2 points. And then the consequence is that by going back and forth, it can actually reduce the maximum number of the two counters. We call it a shallow path. Okay, so shallow path means that we can limit the maximum number of these counters to, we can actually bound the maximum numbers of these two counters. Okay, so the idea can be essentially described using this figure. So recall that in the D1 reachability computation, right, in order to make it decidable, we want to bound the maximum depth of parentheses and bracket. And we want to, for any path in your original graph, and we want to construct, it's possible to construct a shallow path. So let's take a look at this example. So in this example, we have a node, we have a graph with 3 nodes and several edges, okay? And it contains 2 cycles. So the first cycle contains 5 open parentheses, 5 open brackets. Second cycle contains 7 closed parentheses and 6 closed brackets. And there exists a path from A to C. Okay, how how is that possible? Because we can solve this simple linear, like equation systems, right? So the first equation corresponds to the parentheses. Okay, that's a 5, 5 and 7. So 5x and y, 7y. And the second equation corresponds to the bracket. And of course, we want to ensure that nothing goes negative. But in this example, it's always the case. Okay, so if we can solve this equation, then we can conclude that there is a path from A to C. Okay, so here x is 5 and y is, x is 7 and y is 5. Okay, so if we take a deeper look at this path, okay, assume that we want to bound the maximum depth to 23. Okay, assume that this is our threshold. And this is certainly a non-shallow path, because if we take a look at this path, from A, we have to go through the first cycle 7 times, and then from A to B, and then go through this negative cycle for 5 times, and then we can reach C. Okay, and at this point, okay, we beyond this. We are beyond this 30, the maximum depth. So we are at 37 and 37. Okay, but as I mentioned, due to this special bidirected setting, we can go back and forth between A and B, which makes things more interesting. Okay, so let's see a slightly rearranged path. Okay, from this path, instead of going this first cycle for 7 times, that exceeds this threshold that we will not bound, we go through this cycle for 6 times. And if we go through this cycle 6 times, we are at 30 and 30, which is below this threshold, right? By definition, it could be a shallow path. And then we go from A to B and use this negative cycle to consume some positive values. Okay, then we will be at 23 and 23. Let's go back and forth. Okay, then we go back to the original point because the graph is bidirected, right? There always exists inverse edge. In this case, that's the open edge from B to A. So if we're at A, we can continue to consume the additional edge, right? And then go to A and then continue the process. So if we take a look at this path, we can see that the maximum value of the two counters will stay below 23. That's that we call a shallow path. Okay, and that basically shows that given an arbitrary path, due to this bidirected setting, and also due to the fact that we are working with the D1 reachability problem, it's always possible to somehow compute a shallow path. And we can use the bound established in the shallow path to make the problem decidable. So indeed, the result is that the bidirected D1 reachability problem is decidable in polynomial time. And in last year, we came up with a result to show that there exists a polynomial time algorithm to solve precisely the reachability problem. Okay. And interestingly, and this year, this result has been improved to cubic time, almost a cubic time. So if you are interested in this result, and please feel free to come to join the Wednesday's session, where we will be the authors will be talking about a smarter way to do the reachability computation. Okay, that summarizes the first direction. And then the second direction is that, again, if we take a look at this diagram, so we can see that previously, all of our discussions focus on the static version of this graph, meaning that we assume that we have actually read the graph before we do the computation. But in reality, the graph can be on a sequence of edge insertions and deletions. And it is an algorithmic foundation for performing interactive program analysis. It means that your analysis should be able to respond to code changes, right? You can insert code and delete code to your program. So this is the static view of graph reachability, where we have the graph, and we know all the edges in advance, and we also have the grammar, and we have the algorithm for solving the problem. And in a dynamic setting, now a user can remove one of the statements that corresponds to the removal of edges in your graph, okay? And in this case, how do we solve the reachability problem? How do we maintain the reachability information efficiently? Okay, This is called the dynamic graph-reachability problem. And in this case, we can first focus on the bidirected Dyck-reachability problem. So to talk about the dynamic problem, graph-reachability problem, we have to consider three aspects: the cost to perform pre-processing, the cost to perform the update operation, and the cost to perform query. So pre-processing means that, of course, you will begin with an initial graph, right? Possibly empty, but in some cases, it will be a non-empty graph. What is the cost to compute some initial information for your input graph? The second operation is the update. So upon any edge insertion and deletion operations, and how do you update the corresponding reachability information, and also the cost associated with the query. So at any time, I am allowed to query your data structure to see whether or not two nodes are reachable. So there exists a naive way to somehow approach this problem. So the first naive way is that we do nothing for pre-processing. We do nothing for update, okay? But whenever we have a query, we apply the optimal Dyck-reachability algorithm so that we can solve the problem. So in this case, the query complexity is out of M. The second naive way to do it is is more eager. That is eager. And for the pre-processing, so we do everything for the initial graph, and we do everything whenever we see an update. So the benefit is that whenever we want to answer a query, now the query costs only constant time. Okay, from this existing naive or straightforward approaches, we can see that there involves a lot of redundant computation, right? Because if you query something, again and again, there must involve some redundant computation, right? Because here you are blindly applying the reachability algorithm. And in this case, it's the same thing. Whenever you have an edge insertion and deletion, you are basically recompute, some information in your graph. So, somehow we came up with an interesting result that we can avoid this redundant computation. So the overall complexity is that for the pre-processing, of course, we cannot beat the optimal algorithm. So it takes out of n time to do the pre-processing. But for the update, okay, instead of run the optimal Dyck in a straightforward manner, we can run, in a smarter way so that we can guarantee that it only takes out of n time, where n denotes the number of nodes and m denotes the number of edges. And it supports constant query. It's constant query. So if you are interested in the result, please do not miss the talk in the same section, on Wednesday. Okay, so that concludes the tutorial. So to wrap up, and in the tutorial, together with part 1 and part 2, we have talked about the past and present of graph-reachability-based program analysis. Especially, we have been focusing on discussing the theoretical aspects of graph-reachability, and Tom has also introduced several interesting client applications. And in the second half, we talked about several ways to deal with the undecidability. And finally, we talked about several interesting future directions. So we didn't somehow, due to the time constraint, we didn't get a chance to talk about applications, but hopefully, I hope that by attending this class, you will be convinced that graph-reachability is an interesting problem to solve, and you can apply graph-reachability to many underlying interesting applications, okay? So the second type of summary is more like a personal note, okay? So personally, I find working in this direction very interesting. So my own journey starts with this fast Dyck algorithm when I was a student. And several, 6 years later, and my result has been improved to linear time, okay? So this is a big leap, and somehow if you are involved in this process, you will be more than happy to see that your result has been improved by other researchers. Okay, for the second result, the same thing happens. Originally, we came up with an algorithm based on graph simplification algorithm based on fast Dyck, and then later on, with some references, we are able to improve the algorithm to linear time with the current state-of-the-art knowledge. That's also another joy of research. And finally, I'd like to conclude that for the bidirected Dyck-reachability problem, that's the same thing. So last year we showed decidable variants where the complexity is not very nice. But this year the result has also been improved. Okay, they are exactly the same. Of course the result presented in this year's POPL is richer, but I'm only talking about one specific problem. So the complexity has been improved from n to the 7 to the qubit time. So I'd like to conclude that by doing this type of research, and you will find it very rewarding because you can learn more knowledge by studying someone else's new result. And also at the same time, we can see that the field is developing, and we will continue seeing some new results and make this field more and more useful, and so that we can attack more and more problems in practice. Okay, so that will conclude my talk, and I'm happy to take any questions. And thank you very much.
Thanks.
Hello, so I've got two questions. The first is a really quick one, just because I don't know if you mentioned it, but for Chatterjee's result, we know that it's asymptotically faster, but experimentally, is it also empirically faster? Just because you didn't mention it.
So which one? You mean the
optimal
Dyck?
Dyck versus fast
Yes.
Dyck.
Exactly. Yeah. If you check the paper, the practical performance is also better.
Yeah, yeah. Mm-hmm. And then the second question is just a bit of a stupid question, probably up there with the stack question there. Mm-hmm. If we are just thinking about the call graph example, what prevents us from just doing the analysis function by function, kind of like Rust's borrowing? So we take the return value of the function, we show how the return value of the function potentially depends and or aliases and or taints from the arguments, and then we also associate with every function a frame of any global variables it may do, some kind of frame rule type thing, and then we just inline that graph every time. What prevents us from doing that?
Yeah, that's a good question. So to answer this question, I'd like to address 2 points. First, I think in your example, you're showing Rust. So Rust has a very special and restricted linear type system hierarchy. So it's possible that this restriction introduces additional constraints so that it may simplify the problem. So it will make your idea viable. Okay, that's one point. The second point is that in principle, it will be very difficult to do it for general languages like C. Why? Because in the presence of recursive functions, okay? So if the function, right, I mean, think about two, mutually recursive functions, right? One depends on the other, then it will be difficult to summarize the effect of the function to perform this bottom-up computation.
Why not take the mutually recursive functions and, for the purposes of the algorithm, just inline them into each other? So just because any recursive function can be transformed into a loop with a stack, of course.
Yeah, so that's basic. Yeah, I think I see your point.
It would still be an approximation, but the inter-Dyck algorithm is itself an alias approximation anyways. So
yes. So that's basically, I think you are talking about one way to solve the problem. Yes, you can model everything as a graph, and then you can apply the reachability algorithm for solving the reachability. Okay, you can also somehow. Maybe it's also possible to somehow use this bottom-up strategy where you first focus on the bottom functions and do the summary. Okay, so the point I want to mention is that if you take a deeper look at the summary-based CFL-reachability algorithm, you will see something similar. Because essentially what CFL-reachability, at least Dyck-reachability does is that first it will begin with some Dyck-reachable node pairs, and then look for open parens, closed parens, and generate new summaries. And that process, to some extent, is simulating the, what you mentioned. Okay.
Just a really quick note. Have you heard of the work on RVSDGs, so regionalized value state dependence graphs?
No.
Oh, okay. It's just interesting because it's a graph-based representation of programs that uses a similar kind of trick, though I don't know how far they go with it.
Okay, yeah, I think we can talk it offline. Yeah, thank you.
Hi, thanks for your talk. I have two questions. The first one is on the paper about the shallow paths, where there will be circles on the graph and there will have some number on the edge. I'm wondering if it's able, like the analysis algorithm still able to cover if the number on the edge is symbolic, like not a const number. It seems in the example it's only 3, 7, it's const. If the number is symbolic, it's a variable, it can only know during the execution.
So to answer your question, and the example that we show in a tutorial as a paper only shows that it's possible to compute a shallow path. The definition of shallow path is that the depth is bounded by a certain value.
I see.
Okay, it doesn't matter in practice. It doesn't matter if it's a 5 or 6. It just shows that it's bounded. I believe it's n to the maybe 6 or something. Okay, it's bounded by that, meaning that in order to compute this reachability, your problem, at least, well, in the worst case, you need to expand the graph to this maximum bound. Then you can compute everything. So the counter, the value of a counter actually doesn't matter. It only shows the upper bound so that the problem is decidable in polynomial time.
So what if I don't know the number then the number is a variable. It like comes from other inputs.
No.
It doesn't matter?
No. It shows an upper bound. It shows an upper bound of the depth. Okay, let's say if your upper bound is n to the 7, okay, n is the number of nodes. Okay, if the bound is n to the n to the 6, all you need to do is to expand the graph expand the graph to all the way down to n to the n to the 6. In this expanded graph, although it's ridiculously large, but still you can solve the reachability problem based on summary-based computation.
I see. So you are expanding it's more like expanding the graph for so many times.
That's the essential idea, yes.
Okay. And you will need to have restriction on the number, like bound on the number.
Yeah, that's formally stated in the paper.
I see. And the second question is a high-level question. It's the last two paper. It's the improvement seems from the n to power of 7 to n to power of 3, which seems a huge improvement. And so I'm wondering, the two paper, this complexity, they are solving exactly the same problem?
So as I mentioned, right, this new POPL paper is addressing a richer set of problems. Okay, it's considered something else, like I believe DK or something else. So here I'm only talking about that for that specific problem, bidirectional D1, for that single problem, it has been improved from n to the 7 to n to the 3. Yeah, you're welcome.
Thanks for the great tutorial. I thought it was very extensive.
Thank you.
You mentioned two lower bounds. One was the lower bound for context-free language recognition and Q. And then you also mentioned the 4 Russians algorithm. Is that an approximation or is that an exact algorithm?
That's a good question. Okay. I'm very glad that you raised this question because it corresponds to it has connections with your earlier questions, right? So, in general, from an algorithmic perspective, there are two types of algorithm. One is called a combinatorial algorithm. Second is called algebraic algorithm. Okay. The fast CFL recognition, subcubic time CFL-reachability, subcubic time CFL parsing based on Boolean matrix multiplication belongs to the algebraic approach. Okay, so the drawback of this line of work is that it's not very practical. Okay, so yes, you can achieve a subcubic bound, but it's not practical because there's a huge hidden constant. And what I mentioned in the tutorial is the combinatorial algorithm. Okay, like for example, Boolean matrix multiplication, right? Yes, it can be solved in subqubit time, right? That's the faster matrix multiplication, but it's not practical. It's the algebraic approach. In practice, what we do is the qubit time, right? Although it's, arguably the complexity is worse, but in practice, sometimes it works well. Okay, so this naive Boolean matrix multiplication-based algorithm is called, in the loose term, is called the combinatorial algorithm. So the result states that there doesn't exist any combinatorial algorithm that runs in subqubit time. Recall that in the definition, right? If you check the paper, the definition of subqubit is n to the order of 3 minus epsilon, is a constant. That's slightly better than whatever logarithmic factors that you can save. Okay, I hope that answers your question.
Yeah, and the second lower bound you mentioned was, well, the decidability result for shuffle duck languages, and is shuffle duck language the same as an interduck language?
Yes.
Okay. So then I know there's a result that shows that you can recognize a shuffle duck K language, like a shuffle duck N, where you have a preset number of parentheses. You already know the brackets, and you can use a counter automata to recognize that.
Yes.
I'm just having a hard time reconciling this counter automata result with the undecidability of interduct.
So first, I think I'd like to clarify a few things, right? So you're talking about parsing, and here we are addressing reachability. Okay, reachability problem is more general than parsing, right? Think about the CFL parsing and the CFL reachability. So the idea that is applicable to language parsing problem may not be immediately applicable to the reachability problems, okay? Second is that I believe for indirects language, we only know that, yes, I think, although I think I didn't mention it, but for the D1, we actually do not know that whether or not it's a lower bound. Right? We only show that this problem is decidable in polynomial time, and previously we gave a 7, n to the 7 result. And the lower bound result mentioned in my slides applied to CFL-reachability and Dyck-reachability, not indirects-reachability. Okay, yeah.
Yeah, sorry, this probably shows my ignorance, but are the complexity bounds and or decidability improved then if the graph is assumed to be a DAG? Because, I mean, at least intuitively for the DAG case, that would make it decidable, right?
For that, for indirect case, I'm not sure. But for the CFL-reachability problem, if you refer to the original like the, parts, like the graph theoretic method for database, the very first paper, well, not the very first, but among the first few papers to introduce CFL-reachability, you will see a dedicated paragraph to talk about the CFL-reachability problem instance on DAG.
I think, can we deduce that interdike is decidable for DAGs because between any 2 points on the DAG, we can just enumerate all the paths since there are no cycles, so there can't be any infinite paths, and just parse each path. So it would be exponential time, of course, but
yes. I think that's possible. Okay.
Actually, would it be exponential time? No.
Well, so first, I think that's possible, but in order to show the result, we need to have a formal, like we need to have a formal proof. Okay. And then the last point I want to mention is that yes, I mean you can find some improved result on, sub problems. Okay, but as I mentioned in the class, as I mentioned in the tutorial, right? Whenever you identify sub-problem, you need to also make sure that this sub-problem makes sense, meaning that it's meaningful to consider this problem in practice.
It's because you mentioned Rust's restrictions, and I did a lot of work with lifetimes, and you can reduce lifetimes to basically a kind of DAG aliasing condition. And so I was trying to see how this kind of alias analysis would work in like the DAG setting. So my intuition is that it is decidable, but I need to think about it.
Yeah, so with that, it will make this problem interesting. And I believe that, by a quick thought, I think it should be, yes, I think it should be decidable, because if you can check Tom's original paper to show the undecidable result, that 2000 paper, and yes, actually you need to construct very special, cycles and to somehow simulate the PCP problem. if you don't have cycles, I believe that maybe, first, I think if you don't have cycles, maybe you are not able to establish that the problem is undecidable. So it means that maybe it's able to show that the problem is decidable. Very likely.
I mean, is there something wrong with like the informal argument that just like in a DAG, there's a finite number of paths, even if it's very large, between any two nodes, and the inter-Dyck parsing problem is decidable for a path, like for an individual string, and so therefore we can prove it is decidable by giving the very, very bad algorithm in which we iterate through all the paths and perform the inter-Dyck parsing algorithm on every path, so therefore it's decidable.
I think it's the way to go. But I'm not sure if it's decidable in polynomial time.
That would be the interesting thing. But like, we know it's not an undecidable problem anymore, so
Well,
now we can optimize.
To be more rigorous, right, we need to formally show that it's, I think it's likely that it's decidable, but we need to, we need a more rigorous argument. Although I'm with you, I think it's decidable. But
I mean, like, minus the mathematical notation, what's missing from that? Because I mean, if there does not exist a path between any two nodes that passes the inter-Dyck parsing, then we know that it's unreachable. If there does exist a path, then by definition we know it's reachable, and there's only a finite number of paths to check. So how much further do we have to go there?
Yeah. So my point is that to establish the proof, we need to, treat it in a more rigorous manner. Okay. Yeah. I think that your argument makes sense, but in order to establish a formal proof, and you need to consider maybe corner cases, and maybe you're missing something. I'm not sure, but I think it's very promising.
Any other questions here? I think there's no questions from remote audience, so I think that's today's tutorial.
Okay, thank you very much.